And now we're moving on to Denis Villemonais.
Hello.
Hi.
Do you hear me?
Do you share your screen? Yeah.
Yeah, share my screen, of course. Okay, can you see my screen? I think I cannot do better than that.
Yeah, that's fine.
Full screen. Okay.
Okay, and so the second talk of this first session of the afternoon, we have Denis Villemonais, who's going to talk about almost sure convergence of measure valued Polya processes.
Okay, thank you. Well, thank you for the invitation to this meeting, and not in Bath, but it's still nice to be back in Bath in some way. So today I will speak about almost sure convergence of measure valued Polya processes. This is a collaboration with Cécile Meyer. So this is perhaps slightly different from several other talks, since I will keep things relatively simple and perhaps not that much application oriented. So, but well, that's what I do. So first, I will recall what is a quasi-stationary distribution. I'm trying to give simple example to get the sense of what it is. Perhaps everybody already knows that, but I will repeat. And then I will introduce the measure valued Polya processes, their link with quasi-stationary distributions, and their link with a certain approximation scheme of quasi-stationary distributions. So first, a simple example. I will start with just a situation that everybody knows well. Consider a Markov chain Xn on a finite state space whose transition probabilities are, for instance, given by what you see on the screen. So this Markov chain is irreducible, as you can see, and it is aperiodic because of this small condition. And hence, in this case, it is well known that X admits a unique stationary distribution, US, that it is a left eigenvector with respect to the transition probability matrix P with eigenvalue 1. And also that for any initial distribution mu times P to the power n, where mu times P to the power n might be interpreted as the law of Xn under P mu converges to nu S. Okay, so this is well known. This is a consequence of, for instance, of Perron-Frobenius theorem. And there are well-known extensions to more general state space using either the spectral theory ID, so using the fact that you have an eigenvalue 1 and then a spectral gap, for instance, and also using more probabilistic oriented method. So coupling methods, irreducibility assumptions, and also Lyapunov, Foster-Lyapunov type criteria, and so on. And there are many other ways to study this kind of things, of course. Okay, so in order to speak about quasi-stationary distribution, not stationary distribution, we look at a similar setting, but with Xn, Markov chains evolving in the state space 1 to n with an additional point 0. In this case, transition probabilities, let's say Qij, are given by exactly the same one, but with an additional probability of transition from 1 to 0. You know that there is no additional transition probability from 0 to 1, so 0 is an absorbing state. So in fact, you can prove that there is a unique stationary distribution for this process, of course, which is the direct measure at 0. But more interestingly, we know also that X admits a unique quasi-stationary distribution, let's say nu QS. And if I denote by P the transition probability matrix restricted to the points 1 to up to n, then we have, similarly to the stationary case, nu QSP is equal to theta 0 nu QS, where theta 0 is a number strictly between 0 and 1. So this is also left eigenvector, but with a different eigenvalue. And similarly to the previous case, we have theta 0 to the power minus n times mu Pn, which can be interpreted as theta 0 to the power minus n times the law of xn under p mu. The law of xn, maybe I might have added xn restricted to 1 to up to n, okay, is equal so to mu converges to mu of eta. So I think this was also the convention introduced by Pierre Delmoral. Here, mu of eta is might be interpreted as a product scalar between the scalar product between mu and eta, or the integral of eta with respect to mu times nu qs. Okay, so here mu is for any initial distribution, theta 0 is the eigenvalue, and eta is a positive vector or positive function, where e is 1 to up to n. Okay, so in order to prove this result, in fact, using Perron-Frobenius theorem, it's very similar to the stationary case. And as Darosh and Sineta in 1965 observed, because I think they were the first to make the connection between this probabilistic problem and Perron-Frobenius theorem when the eigenvalue is not 1, and it implies, of course, that the law of xn condition to under p mu condition to xn not in the absorbing point converges in total variation norm toward nu qs. So this is the kind of property that we may I was looking for the last years. So now I will speak a general definition of a quasi-stationary distribution, and I will present a general result. So let Q be a positive kernel on a state space E, such that Q is sub-Markov. That is, for all x in E, Qx of A is smaller than 1. And then consider xn. So I decided to present these parts in a discrete time, but other parts will be in continuous time, but really it's very similar. So consider xn a Markov chain evolving in E plus an additional state D, with transition kernel given by the probability starting from x that x1 is in a state is equal to delta xq plus 1 minus delta xqe times direct measure at D. And we choose D to be an absorbing point. That is, the probability that x1 equal D starting from D is equal to 1. Okay, so this defines a Markov chain evolving in E cup D with D absorbing. And for the rest of the talk, I will always denote tau D when I use it as the absorbing time. In this case, it is defined as the heating time of D. And we have, of course, xt is equal to D for all t bigger than 2D, almost true. So there are different definitions of quasi-stationary distribution. A quasi-stationary distribution may be characterized as any probability measure nu qs on E. It's important that nu qs charges E, but not E cup D, such that nu qs is a limit when t goes to infinity of the law of xt under p mu for some initial distribution mu, conditioned to t strictly smaller than tau D. So t strictly smaller than tau D is exactly equivalent to xt different than D with this in this setting. So this is a way of defining quasi-stationary distribution. So in this definition, I insist, in fact, in the limiting aspect. So this might also be a conditional limiting distribution. Okay. So I decide not to cite several papers, interesting papers on quasi-stationary distributions, because it's quite sure that I will miss some. There have been a lot of activity on quasi-stationary distribution, especially during the last 10 or 12 years, sorry. So I will only cite 2 surveys and books that are usually cited. So one survey that I wrote with Sylvie Miller in 2012, simultaneously Vanden and Paulette wrote also a survey, slightly different, with slightly different objectives. So this was also in 2011 actually, but publication time are different. And there was also a book written at the same time by Collet, Martinez, and San Martin. In these books, you can find general results. For instance, a well-known result is that if the convergence in the definition is for all set A, all measurable set A, then you can show that this implies in particular that P nu QS of xt in T plus picto D is equal to nu QS. Okay. So here you have the idea that nu QS is kind of stationary distribution for the conditional law. Okay. So now a general result. So this is a recent result that I obtained, an assumption that we built with Nicolas Champagnat. So there are different objects that, for which the meaning will be clear a little bit later in the slide. And importantly, a probability measure nu and a subset K in E. So typically K is finite if E is denumerable, or a compact set if E is a Polish space, or this kind of thing. K has to be thought of as a compact subspace of E, even if there is no topology and E here, the arguments are not topological. So first we have something that looks like a classical Dublin condition, but local in the sense that for all x in K, so in the subset K, delta x q to the power n1, where n1 is a fixed number, is bigger than C1 nu restricted to K. Okay. And another condition is that nu q and E, which may be interpreted as the probability of survival of non-absorption at time n starting from Q, is bigger than, up to a constant, delta x q and E for all n in N and for all x in K, importantly. So usually for this kind of the first property, Dublin condition, you have a lot of large literature that ensures this kind of properties. For the second one, it is more difficult. It looks gentle, but is not, and it is usually quite difficult to prove.
So, sorry, Danny, can I interrupt? Yes. So the second condition means that if you start with the distribution nu,
yeah,
then the mass that you get in E after n step is bigger than if you start from x time a constant, right?
Yeah, exactly.
What does the first one mean?
This one?
The first one, yes, the left one.
Maybe you're more accustomed to see it this way. The probability starting from x of x n1 in A is always bigger than C1 nu of A. This is really a classical Dublin condition that you get when you apply it.
Oh, okay, thanks.
Sorry, enough time for time. Okay, so next, we also assume some kind of Lyapunov type assumption. So Lyapunov in the sense of Foster-Lyapunov type of assumption. So there are some objects. Importantly, there is a first function phi1 for which we have a condition that really looks like a classical Foster-Lyapunov condition. But we have another condition with a phi2, which is, if you look at the order of the inequality, which is a reversed inequality. And this is different from the usual Lyapunov type assumption. And what you see here is that, importantly, so phi1 smaller than theta, delta x q phi1 smaller than theta 1 phi1 typically means that the process as the return time to K for the process typically has moments of order theta 1, well, just below theta 1. And then so you have this kind of return condition on the return time times to K. And it's on K that you have the Dublin condition. And for the second one, it's slightly different, but you can, if you take phi2 equal 1, for instance, the simplest case, phi2 equal 1e, then this is simply that the probability of survival of the process during time 1 is bigger than theta 2. And hence what we say essentially is that the probability that the process survives for time 1 is bigger than the typical speed of return to K for the process. Okay, so we have these two things. And under these two conditions, what we proved with Nicolas Champagnat is that in this case, there exists a quasi-stationary distribution, and there exists alpha constant in 0, 1 and a constant C, such that for all f smaller than phi1, and in particular for all f, which is an indicator function, the expectation of fxn under p mu conditionally to the fact that the process is not absorbed at time n, converges to nu qs of f at speed alpha to the power n with a constant that depends on the initial distribution of the form mu of phi 1 over mu of phi 2. Okay. So, okay, so there are a lot of other similar results that appeared just after 2017, very similar results that appear after 17, either by me and Nicolas or by other peoples. I do not present all of them because it's not the main subject of the talk. It's just that I want you to know this one because it will be linked to the main assumption of my work with CC.
Sorry, and you have any idea about alpha?
Not really. I mean, you can look at alpha, and it is probably true that it is dependent on, yes, it is true that it is dependent on all the quantities appearing in assumption E, including the supremum of phi 1 over k, the infimum of phi 2 over k. But we decided not to look at the dependence of alpha over on these quantities because it's ugly and clearly not optimal.
Okay, thanks.
So really, to get a decent alpha here, for me, is still an open question. I mean, to get something that is close to the second eigenvalue. Actually.
Yeah, maybe you need to optimize on phi 1, phi 2 or something.
Yeah, maybe, but maybe it does not work that well. But maybe it's possible to do that. Yeah, right. I don't know.
Interesting. Thanks.
Okay, so what is the main point of the proof?
Denis, just one question.
Yes.
Is it the second eigenvalue or is it the ratio of the second over the first? What do you expect here?
Yeah, the ratio, you're right.
Yeah, okay.
The ratio, yeah, completely. Thank you. Yeah, sure. So the main point of the proof is to use a very easy generalization. I mean, the generalization is easy. The first result is very clever of a method provided by Herrer and Mattingly in 2011 to prove that if you have some time-dependent function, so maybe just first focus on this guy. It's just we look at a semi-group. Okay, the semi-group here is the semi-group of the process starting at time n and conditioned not to be absorbed before time n plus m. Okay, and it appears that this is a time inhomogeneous semi-group. And what we want to do is to apply a Lyapunov type criterion to this time inhomogeneous semi-group. And actually, implementing just arithmetically proof in the time inhomogeneous setting just provides us what we need. So we want to prove this kind of property. Okay. I will not detail how we prove this. It's not the point, but maybe just to do so, we have to prove various estimates on, and there are two very important estimates. The first one is the expectation of phi 1 of xn. When I don't write an indicator function, it's always phi 1 of xn when taking phi 1 of d is equal to 0. Okay, phi 1 of the expectation of the cemetery point is 0, divided by expectation over x of phi 2 of xn. So we can see why, because if you get a good estimate on this quantity, then you typically get this last set of inequalities. And this is nice. And it's easy to understand why if you just consider a simpler situation. Imagine a situation where phi 1 is a norm-like function with compact level sets. It's not the case in no situation, but it helps to understand. Then you see that the integral of phi 1 with respect to the conditional law is uniformly bounded in this case for a given initial point x. And this gives you tightness, I mean, in the Polish state at least, and if phi 1 is a lower semi-continuous, this gives you tightness of the sequence of conditional laws. So from this point, you see that you at least have limits for your conditional laws. Okay, so these are the two main points. Okay. I won't go further because the proof is a little bit long and it's not the main subject of the paper. So we can apply this criterion, in fact, even a more precise one, to the neutron random walk. So here the neutron random walk, I think everybody is okay with that, but it's a simplified version because we saw a lot of things. So just consider E to be a bounded regular domain of Rd, R2 even, and S to D-1 the unit sphere. So for me, the neutron random walk is a piecewise deterministic Markov process in Rd times SD-1. Rd is in fact in E times SD-1 maybe. So the first component is the position, the second one the velocity. So first the process starts from a point X, and then it chooses a direction in SD-1. Okay, then it evolves in this direction, and so on. Sorry for the sliding, it's the slides, but it's cannot do otherwise. Yeah, and the process evolves, and so on and so on. And at some point, the process will finally hit the boundary with probability 1. And at this time, I consider that it is absorbed and it is sent to the symmetry point. And under some density conditions on the law of the resampling of the distributions and the law of the rate at which the process stops and decide to redirect, choose a new direction, some condition on it, then we can show that there exists a quasi-stationary distribution and alpha. The one that we have sees convergence. So notice that here we don't have the mu phi 1 over mu phi 2. So it's slightly better because typically phi 1 is not bounded from above and phi 2 is not bounded from below. In fact, so to do this, we use another paper that I wrote with Nicole Champagnat, but I didn't present, but which is actually a sub-case of the general one that I presented. Okay, so we have these, and we know that so the neutron random walk admits a unique quasi-stationary distribution. Okay. So now the question is, how can we try to find a numerical scheme to estimate this? So the idea behind the numerical scheme, I will draw this because it's easier. So consider a simpler case with E, okay, which is just one-dimensional. You have the time. And we look at a process that evolves as follows. So it starts from an initial position x0. 0 will be the absorbing point. The process evolves, and when finally it hits 0, instead of being absorbed, okay, it is sent back it is resampled according to a uniform point uniformly chosen in the past. Okay, for instance, let's say choose this one. Okay. And then I let the process evolve and does it again. Maybe may choose this time this point. And so on and so on. Up, maybe might choose this one. And so on. Okay. So you have this kind of reinforced process, reinforced because the process depends on its past. And what we're looking at is typically also, this is not xt, it's yt. So okay, and what we're looking at is typically things as integral z over t of the empirical distribution of yt. Okay, and the question is, does it converge when t goes to infinity? And toward which quantity? Okay, and in which sense? Okay, so this is the algorithm in a simple case. So if we do it in a more general setting, we can consider xt a Markov process evolving in a state space E with gap D with D absorbing. We fix a quantity T. So this is something that I didn't do. I didn't do before, but we need to fix a limit in time T and consider the following self-reinforced process with state space E. So as before, the process starts from a point X. It evolves according to the dynamic of X. X is the absorbed process up to time tau 1, the first time of absorption. Then at this time, y1 is resampled. It doesn't stay at D, and it is chosen uniformly on the path trajectory of y. That is, y1 is equal to yu1, where u1 is uniformly distributed on 0 to 1. Okay. Then again, y evolves according to the dynamic of x up to the minimum of τ1 plus t on the next absorption time, and so on and so on. And we are interested, as I said, about 1 over t in the historical empirical distribution of the process. And we want to prove in some situation, more situation, when in the situations we are interested in, the convergence of the historical empirical distribution towards the quasi-stationary distribution, when it exists, of course, of the process. So, natural question is this always true under reasonable conditions? Well, I don't know, and as far as I know, there are no general answers to these questions. But there have been several works on the problem. I think the earlier one, but I may be wrong, is a work by Aldous, Flannery, and Palacios in 1988, when E is a finite state space. And this is particularly interesting for this talk because it made use of the link between polyahertz, irreducible polyahertz, and quasi-stationary distribution. Then, way later, there may have been some work in between, but the one I know the best. So recently, actually simultaneously, Benaim and Cloez and Blanchaglin and Zeng reproved this kind of result for finite state spaces with some refinements and using a different method based on stochastic algorithms. Then Benaim, Cloez, and Ponu generalized this method to processes on compact spaces, discrete time processes on compact spaces. Recently, Andy Wang and Roberts and Steinsaltz proved that the result works if the process is resampled, but not uniformly on the historical path of the process, but with a time-dependent distribution. And it works too in this case. Okay. And then recently with Cecile, and this is the works that I hope I will have time to present to you, we proved that this works for processes in non-compact spaces, but importantly, without hard boundary. This is important. So there is a difficulty for processes with hard boundaries. And okay, recently with Michel Benaim and Nicolas Champagnat, we proved that it works for diffusion process in a Boolean open space, absorbed when they hit the boundary, so with a hard boundary. However, none of this result applies to the neutron random walk. And actually, for the neutron random walk, as far as I know, even in the simple case I presented to you, it is an open problem to know whether it works or not. This is an active area of research. Okay, so another natural algorithm, but that has already been presented, I think, several times, is a Fleming-Viaud type process. Maybe it's the first time it's called this way, but maybe it's the last time it's processed, because Fleming-Viaud type process is not related to the Fleming-Viaud process, which is a little bit embarrassing. One may prefer the Moran particle system or to include other name in the definition of the process. So maybe I will go quickly on it. The main point is that, okay, there are early references on the algorithm. I think most of them have been presented. This is the one where you resample according to the empirical distribution of particles, simultaneous particles. I made some personal contributions to this area in general state space, including hard boundaries, but it doesn't work for the neutron random walk. But there is a way to make this work for the neutron random walk in a work that I did with William Safran. But actually, this is more of theoretical interest, and I think I can practice the works of Del Moral largely covers most of the cases. Okay, I don't insist on that. I don't insist on why it is not defined. I have up to 5:30, that's it.
Yeah, you can get a bit longer as well, because
okay.
We started later.
So I will go back to this algorithm and why
4:30 Brexit time, but we're and Andrea Zoya is going to do a little bit of a 10 minutes at 4:30.
Well, we also started 5 minutes later with Denis, so I was just going to give
Oh,
him the
did we?
extra
Okay,
5.
yeah.
Okay. Maybe I will be done before 5 minutes after my allotted time. So, okay, I continue. Okay, so now I will speak about measure valued Polya processes. So first, I just will remind you what are finite and irreducible polyatoms. So there are different definitions. There are the classical polyatoms that do not enter in this setting, but these are the irreducible ones. So we start with the urn at some time n, and we have an initial composition of the urn at time n with blue balls, white balls, and black balls. And what we do is that, so we pick a ball at random, and we have this replacement mechanism. Replacement is that at the time. So, for instance, if I pick a blue ball, then I put back the blue ball, and I add also 2 black balls and 1 white ball. If I pick a black ball, then I add back the black ball, and I also add a blue ball and a white ball. And if I pick a white ball, I put back the white ball, and I also add 2 blue balls. Okay, this is simple. For instance, if I pick the blue ball, then I will add 2 black balls and white ball, and so on. Here I pick the black ball, I have these things, and so on, and so on. And then the state of the urn evolve. So this is a way of defining it, of presenting it. There is another way of formally presenting it. It's to look at the composition of the urn at time n as an empirical distribution of colors. That is, I can say that at time n, I had 3 blue balls, 3 black balls, and 2 white balls. So I say that Mn is a probability measure on E given by the blue, black, and white, the colors, which is equal to 3 direct measure on blue, 3 direct measure on black, and 2 direct measure on white. Okay. And then I pick a color according actually to Mn renormalized. That is, I pick yn plus 1 according to, for instance, with probability 3/8, I pick a black ball, for instance. Okay. We then get the state of the urn at time n plus 1 via this formula. Why? Because, for instance, if I pick yn plus 1 equal blue, then I will add the first line here. This is for blue, black, white. I will add the first line of this matrix. And then Mn plus 1 will be equal to 3 delta blue plus 5 delta black plus 3 delta white. So the first, so there is this famous paper by Aldous, Flannery, and Palacios on this type of urns. Then later there have been refinements on the properties of this process by Svante Johnson, and there are also references to this and other references to this type of results in the survey on reinforced process by Pimentel. And recently, in 2017, simultaneously, Pandyopadhyay and Thacker and Meyer and Markert proposed this kind of point of view on Polya urns to devise of a general Polya urn process on a general state of colors. It is now, here the colors are blue, black, white, classical ones, but now the colors are simply a Polish state space. And it has applications. So as you can see, I will now formally describe the measure valued Polya process. So let E be a Polish space. For the construction, we don't need it to be a Polish space, but it will be helpful to have the result. M plus the set of positive measures on E. And so we need the initial urn, M0, which is a positive measure, finite positive measure on E. We need a set of independent, identically distributed random kernels from E to E, P a kernel from E to E. And then the urn Mn being defined, we define the Mn plus 1 recursively by picking Yn plus 1 according to the law Mnp over Mnp, and defining Mn plus 1 is equal to Mn plus delta Yn plus 1 times R. So if you pay attention, you see that in this presentation, in this definition, contrary to the previous one, R may be random, but in fact, this is something classical for this type of processes, at least when E is finite. And we sample according to MNP over MNP instead of Mn over Mn. So the idea behind this generalization, we will actually use the first one. We will need to have R random. Is simply that, okay, so I represent the space of colors. I start with a uniform distribution over this patch. And I want to be able to pick Y1 outside of the patch. Okay, so in order to do that, for instance, here, and in order to do that, I need to have this kernel P in addition. Okay, so this is another to allow this kind of procedure. And R random allows to have different shapes, different volume of the masses for the M0, even if we pick 2 times the same color. And then the question is, do we have convergence of this process, in the sense that if I look at Mn over Mn of E, the normalized Mn, does it converge with when n goes to infinity, and what is the limit?
Sorry, can you come back? So this is Julien. I have a naive question. You don't renormalize Mn plus 1? It looks like the mass is increasing here.
Yeah, exactly. The mass is increasing, as you can see here, actually. But what we look at is, oh yes, when I look at the limit, exactly, it's the limit of Mn over Mne.
Okay, and I don't understand the role of Rn plus 1 here. Why do you have a kernel? Because M looks like it's a measure.
Yeah.
And then you have a Dirac mass time transition kernel. I'm not sure I understand.
Yeah, so if R is not random, forget the randomness, okay? So this is really just a measure.
Okay.
See, for instance, R may be the Gaussian kernel. So maybe this might be more easy to understand if I wrote this quantity.
I see. So it's like a little measure around the point Yn that you
exactly.
Okay, I see. Okay, thanks.
Yeah. So now we have these hypotheses. Hypothesis C. I gave the same name as in the paper. That's why it might be a little bit odd. But so this is now hypothesis C. So we assume that there is constant C1, C2, theta, and we have that setting Rx is equal to the mean of the random transition kernel. We need that the minimum mass of Rx is bigger than some C1, and that the maximum mass is smaller than 1. Actually, finite is sufficient. We can always go back to the case smaller than 1. Okay. And we assume that there exists theta. Theta has to be smaller than C1. It's very important. Strictly smaller than C1. And that we have Rxv smaller than theta Vx plus C for X. Here, V, I didn't say it, but V is a function with compact level sets. And then we assume also that the Markov kernel R minus I, the sub-Markov kernel R minus I, admits a quasi-stationary distribution nucleus, and that we have uniform convergence in total variation norm in a good subspace of M1 and other technical conditions. Feller, R has to be Feller, and we need some technical Bose-on moments of Rx1, but in our case, it will be clearly satisfied. And I want you to note the similarities with assumption E. In particular, if you recall the second point of assumption E, it is implied by that, okay, this implies assumption E, hypothesis E, with phi1 equal V and phi2 equal 1. And then if you are also able to check the first part of assumption E, then it implies the second point. Okay, so there is a close relation between hypothesis C and the hypothesis E, actually, assumption. Okay, if you have a question, I can go back to it. And what we prove under this condition is simply that under the condition that M0V is finite, then the sequence Mn over Mne converges almost surely to nu QS with respect to the weak topology. Okay, so we have an answer to the question. So now, how is it related to the approximation scheme that I just presented before, the reinforced one? Well, the thing is, so we start with, recall that we have a Markov process X evolving in E cup D, and we fix T positive. Then in fact, we can consider the initial composition measure with initial measure M0 is equal to delta X0, and then define the random kernel Rx1 is distributed as the empirical path of the process up to time T minimum tau D. Okay, and here we see that the law of the empirical distribution of the reinforced process at the nth resampling time is distributed as Mn over Mn. So I would just again try to illustrate it with a small picture. So what you do, you start with delta x0. So this is M0. And then you say, okay, I add the empirical distribution of the empirical path of the process. So this is here Rx01. Then I pick a point somewhere. So here I can pick also delta x0, it's possible. And it gives me y1. So maybe I should have chosen a different name. So y1 for the measure valued polya process. Forget this one. And then it continues, and we add again something that is ry1, 2, and so on. So we see that we can interpret the reinforced approximation scheme as polya. So this is useful, and here we see that the kernels are of course random because the trajectories are random. Okay. So one example where this is useful is, for instance, if X is solution to a stochastic differential equation with B nice, where B has to be nice, so that this has a solution, so that the process is a failure, and we assume that it is killed at rate kappa, where kappa is bounded. And if we denote by Y the reinforced diffusion, then we obtain that if in addition, so you have to assume that you have this drift condition at infinity, okay, then 1 over T integral between 0 and T of delta Y SDS converges in the weak topology, the convergence of weak topology, in the topology of weak convergence, sorry, towards the quasi-stationary distribution of the process, which exists according to assumption E actual. Okay. And so the answer is that, okay, it works for in some situation, but here it's important to note that the killing rate is bounded so that we don't have a hard boundary. And it's important because here we can observe that, sorry, it's not Qx, it's Rxe. Rxe is smaller than T times the probability that τ1 is smaller than T. And in the case of the neutron random walk, and when you have a hard boundary, then this quantity here is not bounded from below, is not bounded away from 0. Okay. Hence, the condition on the minimum of Qxe does not hold true, so our result does not apply. A possible direction. So we had the same difficulty when we tried to work with an elliptic diffusion process killed at the boundary of an open set. And the solution was to prove that 1 over T, the sequence of the family of empirical distributions, historical empirical distribution, was tight. And to do that, we used a very specific argument, maybe already presented, is that you look at your process, it does something like that. Okay. And what you can do is that you can put a reflected Brownian motion below. And you know that the reflected Brownian motion, so it does not interact with this path. And you know that the Brownian motion, the empirical distribution of the Brownian motion is tight, so that the one that is above is tight too. So it's very, very specific. We cannot apply it to the neutron random walk, but there may be another way to prove that it is tight. And when you prove that it is tight and you get the kind of results that we had, for instance, for the neutron random walk with Emma and Andreas, then you can prove that 1/t times the integral between 0 and t of f y s ds converges almost surely toward nu qs of f. Okay, well, nu qs is a unique stationary distribution. So there is hope to make this work, but for now it's not. It's still an open problem. Okay, and this is the end of my talk. So thank you for your attention.
Thanks very much, Denis. Does anyone have any questions? Trying to work out what's clapping and what's happening. I had a quick question. Could you go back to the slide where you had the assumptions? Yeah. So you say that the convergence towards the QSD is uniform in total variation norm. Yeah. Does it really have to be that strong with the total variation norm?
No. What you want is that the convergence is uniform in a distance that is sufficient to characterize convergence. But usually this kind of distance is not. I mean, we use it in the proof, but we don't have any way, for now, to prove this kind of convergence without proving that it converges in total variation norm. So it seems simpler, given the link between hypothesis C and assumption E, to give this assumption.
Okay. And in the paper with Cecile, you prove the version with weight, right?
Yeah, right.
And how does this change the assumptions?
Oh, it's very simple. It's just that here in the assumption, you replace R by Q equal, I don't want to be something wrong, but PR or RP, I don't remember. But I think it's PR. So you just take R, you multiply it by P, and then you have here Q, 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 okay, and so on.
Okay.
That's it.
Are there any other questions? No? Okay, so thanks again, Denis. Can I just ask everyone to unmute themselves and thank the two speakers from this afternoon, please? And then we've had a final last-minute change of plan. I think there was something that couldn't be covered in the discussion session this afternoon, so I'm going to hand over to Andreas.
So Andrea had some beautiful slides, and I just could not let him disappear without showing us these slides. So he was going to give a quick 10-minute whiz round his some of the things that are kind of pertinent at the moment. But they look rather enticing. So just a quick 10 minutes from Andrea.
Thank you. Shall I share my screen?
Yes, please. Yeah.
Okay. Wait a second. Okay. Okay, I think it's full screen now. Okay, can you see the slides now?
Yeah. Sorry, my mic was off.
Okay.
Yes.
Okay. Thank you. So thank you for the invitation and getting some spare minutes for listening to this presentation. I will try to be very brief, and the idea was to discuss a topic which has been under discussion in our group for 3 or 4 years. And the subject is like, how do we deal with particle transport when the underlying medium is not known? We usually say that the media are stochastic in this case. So I will try to give an overview, and I will present some open questions. So let me start with some possible application and motivations for this investigation. In all the presentation that we have seen in the last 2 days, one somehow hidden assumption was that the parameters for the Boltzmann equation and then for the stochastic transport process were perfectly known, like the cross sections and so on and so forth. They were like deterministic. There was no uncertainty on that. But if you look around, there are cases in nuclear engineering applications where you do not perfectly know the stochastic, the material properties for the media where particles are moving around. A typical example, you get a severe accident in a reactor core, like for the 3 Mile Island or Fukushima accident, and you get a mixture of like fuel and water, and you do not know exactly where the fuel is or the water is, and so you get some uncertainty on the material properties. Other examples are like the structure of the materials. If you look at a sufficiently fine scale, like here in for the grain in fuel pellets, you will see that there is a structure appearing, and in most cases you will not be able to describe entirely this heterogeneous scale. This is not the scale of heterogeneity you typically deal with in nuclear engineering applications. It's not like having a fuel at a given lattice position and a moderator like water everywhere else. You are refining spatial scales that are typically very ill-defined. Other application which is very important is like the turbulent layer for inertial confinement fusion. Here is more about photons and not neutrons, but again, this is a stochastic medium. And again, when you take like a steam and water mixture, you typically do not know where the steam bubbles are. So the first question is that, okay, so there is some degree of disorder. Is that important for particle transport? So if you look at this problem from a physicist point of view, the answer will be somehow obvious. In order to get an answer, you must compare the typical scale of disorder with the typical scale of the particle path. How can you do that? Well, we know that we can characterize the typical jump of our stochastic process, and this is defined by the total cross-section, basically, through a given material. Say alpha is the index of the material. You can say that is water or fuel, whatever. So you know that 1 over sigma is what we call the mean free path, is the typical jump length of your particle. And then you must compare this typical length scale to the typical length scale of your disorder. How can we do that? Well, the standard approach is to define what we call rho, the linear density of a given material, which is basically defined as such that if you take 1 over rho, you get the typical linear scale of a chunk of material A in a random mixture. You can see here on the right a given representation. So you basically get 2 different transport regimes, one in which is trivial. So if you take this dimensionless variable xi, which is defined as a ratio between the 2 scales, the scale of the particle as compared to the scale of the medium. If xi is very small, you can say that your stochastic medium, of course, is stochastic, but you don't care. If you look from far away, your medium will look like being averaged. The material properties are homogenized. So this regime is trivial. At the opposite, if you take a very large xi, it means that the typical scale of the neutrons or the particles is comparable to the typical scale of the disorder. And in this case, you expect some non-trivial interplay. So this is the physical picture. How can we go from that to a given mathematical description of what's going on with respect to the particle process? So we will assume, in order to describe this random media, that there exists a collection of states which correspond to the physical realization, and each state is characterized by a given density, so a probability density function of having a given material realization. So you get a map between the material properties at a point and the given point where you look at. So when we say that the material properties are a stochastic object, it means that for the total cross-section, the scattering cross-section, and of course, in principle, also for the source of the particles, they all depend on the typical realization. So you instantiate your material, and for each material point, you get some property which is random. So the final goal in this context would be to compute the ensemble average angular flux. So the angular flux, and sorry about the notation. Notation is like those of that of the physicists and not of that of the mathematicians, but we use brackets as a symbol for ensemble average for our key object, which is the flux. And this is defined as the integral over all possible realization, P of Q being the probability of getting a materialization of phi pertaining to realization Q. What's phi of Q? Well, you assume that when you have realized a single realization of your stochastic medium, then everything is frozen, and then basically for every fixed Q, phi is a solution of the linear Boltzmann equation that we have seen, I mean, all over these two last days. So you recognize the standard linear Boltzmann equation. So this is like the deterministic version, and then you know that if you want to do a stochastic transfer corresponding to this equation, you take the all the exponential flights that we have seen in the last few days. You see that in this equation, we have neglected fission, but of course you can add fission and it will be just the same. I mean, the precise details of the stochastic process are not very important in this context. So what happens now? There are two ways of doing like particle transport in these randomized materials. One is called the Quenching disorder approach, which means basically that we generate an ensemble of n realization from the given probability P of Q. Basically, we are able to create n realization of our random media, and for each realization, we solve the transport equation. We can do that by deterministic methods or by throwing around some stochastic process, but in the end, we get the solution, which is a phi of Q for each realization. And then, given our ensemble of realizations for the medium, we just deduce the flux, which is basically the empirical average over the available realization. This is the standard way and the reference way to obtain what we call the reference solution for particle transport. This approach is in principle exact, but of course the drawback is that we have a huge computational burden, because not only we have to solve the Boltzmann equation, but we have to do that n times for n realization. And if you want to get the histogram and not just the average, and of course your n, the number of realization, must be really huge. The second way, which has been proposed, is the so-called Anil disorder. And then, well, the idea is that, okay, let's write down an equation for the average flux. So instead of like taking the average over the realization, we write an equation for the average quantity we would like to characterize. But you soon realize that apart from very trivial cases, this equation in general is not closed. You basically have a system, but the first moment depends on the second moment, and so on and so forth. So you're in trouble. And what you do is to apply a closure formula, which is more or less justified. And you get, the nice point is that you get an effective transport equation, which is basically written like the regular Boltzmann equation, apart from like some modifications, and this equation is by definition closed, and you can solve it in a single step. So it's like a single modified transport equation. The advantage is that, of course, your computer time will be rather small as compared to the reference solutions, but the price to pay is that this method is just approximate. You have introduced some approximations, and you must characterize them. So what are the typical stochastic media that people in nuclear engineering are working with? One very well-known and very, widely investigated kind of medium is the so-called Markov realizations. What's a Markov medium? Well, in the one-dimensional case, this is very simple to define. So you can get a n-ary. This index n is about like the number of different materials that you are using in your stochastic object. You define some transition rates defined as being the probability per unit length at a position r when you're looking forward or backward along a line. Here you are in one dimension of making a transition between alpha, material alpha, and material beta, and you define that for a given index alpha and beta. And by switching around with the indexes, you can go from like binary, so you have just two materials, to n-ary materials. So you get something which looks like the realization that I've plotted here. So basically you use a Markov jump process characterized by the transition rates between alpha and beta in order to get the boundaries between material chunks. This is very easy, and it has been widely used because it's very simple and it has some nice properties. If you look at the material length distribution, so you measure the typical size of a material chunk with a label, say alpha. So you see what I mean? It's like the typical chunk, the length of a chunk, of a material chunk having a label alpha. This turns out to be a non-homogeneous exponential distribution with a very simple parameter, which is rho alpha, which is just the sum over all the possible transition rates, apart from the trivial case beta being equal to alpha. And the other interesting property is that if you fix a point, say r, and you ask about the probability that at this point you get a material of index alpha, this probability P of alpha satisfies a very simple Chapman-Kolmogorov equation, which is basically a conservation law, which is written here. So because of these nice mathematical properties, Markov media have been widely investigated in one-dimensional case. So the first question is that how can we practically build Markov media in dimension D? Because for one dimension, this is very easy. And until recently, it was like an open question whether one could really create by practical means some Markov media in dimension D. And the answer is that it turns out that it is possible, and we need just two basic ingredients. And the first one is the so-called Poisson hyperplane process, also called the Poisson Tessellation, which is basically a way of partitioning the space and generally in dimension D by using hyperplanes. And those hyperplanes here are distributed according to a Poisson distribution with an associated density F. And each plane here depends on like the normal vector defined as being orthogonal to the plane, and the distance between the plane and some center point in an arbitrary Cartesian frame. So once you get this, define your density for the Poisson process, you can build this Poisson tessellation. Why is that so special? Well, it turns out that once you are done here, you have created your tessellation, then if you draw a line from a point R with a given direction omega, it turns out that this line will be cut into segments that are exponentially distributed with a parameter rho, which we can characterize express in terms of the density F. And since this chord distribution is exponential, then we know that our tessellation is a good starting point to get some Markov property for our stochastic medium. The second step is just to attribute the physical properties. And the simplest way to do that is to apply a coloring procedure by which each polyhedron defined by the planes will be colored, I mean, given a label, say alpha, with probability P alpha. And it turns out that if you do that, you get realizations like those which are shown here. We have worked a lot on like how to practically generate this stuff. And the chord through a given material alpha in your tessellation now will be exponentially distributed with a scale parameter rho alpha, which is simply related, simply proportional to the given rho of the original tessellation. So we are basically done, and we are able to generate the dimensional Markov media. So the open question is that, okay, this is a way of building Markov media. Are there any other, I mean, other ways of building stochastic geometries which satisfy our Markov property? And this is an open question. The second step is that if we go back to the original problem, which was like, okay, now we can generate our Markov media, we can do particle transport for each realization, we can build some reference solution. What about like the second way? So the approximate solutions coming from the Quenching disorder approach. Well, it turns out that if your media are Markov, you can apply a so-called Levermont-Poraning closure. I will skip the mathematical details, but in principle, it turns out that you can close your transport equation for Markov media, and you can write an equation for the material average flux psi alpha, which is basically the average flux in phase alpha. It turns out that the resulting equation is actually a system of equations. So instead of getting to solve the Boltzmann equation, you have for each species, if material, say alpha, you get an equation which looks like the Boltzmann equation, plus a coupling term here, which depends on the other species. So this is written for a binary composition with alpha and beta. What's the physical meaning of this equation from the stochastic point of view? Basically, it means that your particles will have an additional variable in the phase space. So instead of transporting particles according to time, suppose energy, then direction and position, you get an extra label, which is the material label. So your particle will carry also the index of the phase that you are representing, say alpha or beta. And those terms here mean that basically you have to consider an additional term here, which contributes to the total cross-section. So when you are in phase alpha, you basically undergo an additional collision. And when you do this collision, which is basically done with this cross-section rho alpha, which is related to the material density of the medium, then you switch species. If you are alpha, then you go into beta and you find this production term here, which is basically a source term. Okay, so the question is, does it work? Is it a good representation? Because this is supposed to be just an approximation. And we did some comparisons with respect to the reference solutions as a function of the system dimension, from dimension 1 to dimension 3, and as a function of the density rho of the tessellation. And it turns out that if you increase your dimension, your approximation, so this system of approximated equations is becoming better and better. But then if you go from a very dense stochastic material to a less dense stochastic material, then things are getting worse and worse, which was also expected. So the other important open question is that, okay, so we followed some basic rules that we can find in the literature in order to get some reasonable closure for Markov media, but can we do that in a sort of robust way? So can we come up with some approximated effective transport equations that are reliable in order to be predictive with respect to the reference solutions? And this is a true open question. So I think I'm done with this brief presentation. And again, thank you for your time and your patient. So
thank you, Andrea. Actually, so you managed to cover about 15 to 20 areas of probability in one talk. It's phenomenal. This talk has got so, it's packed with so many different things. And actually, the reason why I asked you to do this, I mean, aside from the fact that you took the time to prepare the slides, a few years ago, Martin Hera, who's actually a Fields medalist, I met him once in London, and he asked me to drop by to see him because he was specifically interested in exactly this question. He asked me, he's very interested in SPDs, and his question to me was very simply, does it make sense to consider the neutron transport equation with with noise, let's say, with white noise? Now, that's not exactly the same as what you're asking me, but in a sense it is, because what you're saying is you're randomizing the cross sections, which is, you know, it's kind of, if you think in the diffusive analog of the transport equation, which is of course just the heat equation with a potential, then the normal thing is you add white noise. So okay, you could say, well, it's like putting noise on the Gaussian coefficient as well. But essentially, he asked me this question largely because he didn't know anything about how to deal with it. And I said at the time, I remember saying, I think it's relevant, and it must be relevant because of at least the kind of slush that forms in nuclear reactors. I mean, you gave a much better justification at the start of your talk, the 3 Mile Island meltdown and so on. But I think it's still a very pertinent question. What you are talking about is still fundamentally about a kind of SPDE, but it's SPDEs in neutron transport world, basically. And so there's a big question for me there, is what is learnable from the huge SPDE literature that there is out there? What is transportable into this context, and what is not actually? Because, you know, as certainly my experience with neutron transport is, you know, it really is not anything like the diffusive situation. I mean, there are all sorts of peculiarities to it. So that's the main reason I wanted you to give that presentation. So thank you very much for doing that.
Thank you.
I've succeeded in messing up the program.
Sorry.
But no, it's me.
No.
We were also a bit late as well starting. Alex, where are you, Alex?
Yeah.
No, Alex, the last speaker.
Yeah, Alex.
Shall we? I mean, we actually had quite a good buffer at the end anyway. So, because I was supposed to give some big speech about, I don't know what, Brexit or something. So we can cut the Brexit speech. And shall we take a 10-minute? Do you want to start at 10 past, something like that? We can do and you know, anyone who wants to chat in the meantime, I'll be here.